Hey there, and welcome to AP Chemistry Homework 3A. 3A covers the beginning of the gas law notes, which we did last time. Covered a couple conceptual ideas here in the beginning. We're going to try to run through actually every single problem. Since I'm not there to answer your specific questions, I'm just going to pretend you knew nothing, and we have to go over every single question. So in number one, we have two flasks that are attached via a stopcock, and the right side is evacuated while the left side is full. It is rather difficult to see. Right here it says 2x and x, and that is the volume. It says the volume is 2x for this side and 1x for that side. That is important when you're using your logic here. So the other thing we notice is that there are 6 particles, 1, 2, 3, 4, 5, 6 particles originally on the left side and no particles on the right. So we're just going to talk about first this situation. When the stopcock is opened, the gas is going to start flowing back and forth between the two flasks now that they are open to each other. And eventually equilibrium is going to be reached, in which the gas particles flowing right and the gas particles flowing left are equal. And the quantity of particles on each side is going to be proportional to their volume, kind of like an Avogadro's law, V over N equals V over N. Now those particles are going to spread evenly based on the volume. The total volume will now be 3x, right? It'll be 2x and x. The total volume will be 3x, and those 6 particles are going to be spread out across that. So you take 6 divided by 3, and each x value should receive 2 particles. So the right side, which is x volume, receives 2 particles, and the left side receives 2 and 2 since it's 2x. So there should be 4 particles on the left and 2 particles on the right, since the ratio of volume is 2x over x. Now, if we sealed it, we should be able to test that and prove it. However, there is a random chance component here. If we let this just open for a second and then seal it, it's not going to immediately reach 4 to 2. We have to let a certain amount of time pass. And in any questions like this, we're always assuming that it's reached equilibrium. It's been given plenty of time to get there. The second question is similar, except both sides of the container are x and x, therefore they're equal. So the ratio of particles should be equal. Since it's 6 particles, it should be a 3 to 3 ratio. B was a bit more difficult. Took me a while to think about what I should do. So eventually I used Boyle's law. I said a PV equals PV, pressure times volume equals pressure times volume, to try to estimate what the new pressure would be versus the original pressure. And I decided to say that P equals the original pressure, since they didn't tell us what the pressure was at any point. So I said P times 2x, 2x being the original volume, is equal to the unknown new pressure, there it is as a question mark, times the new total volume. And this is where a lot of people mess up. They did the new volume on the right side, and really it should be the new total volume. New total volume is the 2x of the left side and the x of the right side, so a total of 3x. So when we solve for question mark, we find that question mark equals 2/3 of the original pressure. All right, we would divide the 3 over there, and the x's would cancel. We'd have P times 2x divided by 3x, and we'd say P times 2/3 equals the value. On the right side, the volume is doubling, so the pressure gets cut in half. That's a little bit more cut and dry because we're going from x to 2x. So the pressure gets cut in half. All right, that's number 1. Number 2. Number 2 is good old the Habra process. It's actually the reverse of the Habra process. We're decomposing ammonia back into nitrogen and hydrogen. A and B have 2 very different situations. First, let's look at the reaction. We have ammonia breaking down into nitrogen and hydrogen. We must balance this reaction to make our assumptions correct regarding moles, pressure, and volume. In A, it says that the nitrogen and hydrogen gas are at constant pressure and temperature. So the temperature and the pressure don't matter. So I wrote my ideal gas law over here. PV over NT equals R. And since the pressure and the temperature don't matter, it's all about the volume and the moles. So I wrote, I need to think about volume over moles when I do this. Well, how would the moles change? How would the moles change? Well, the moles go from 2 moles, the reaction occurs, and now makes 1 mole and 3 moles. So it goes from 2 moles to 1 mole and 3 moles. Well, that's really saying it goes from 2 moles to 4 moles. So the volume is going to go from, since the moles go from 2 to 4, the volume is going to double. Whatever the original volume was, the new volume would be double the original. So the new volume is not actually equal to 2, it's equal to twice the original volume, whatever the original volume was. In B is a different situation. I underline the important constants. It's at a constant volume and temperature. It's not a bad idea to underline the constants just so that you're not compensating for them when you shouldn't be. So the volume and temperature are constant. This is just really pressure in moles, which is not an equation we usually think of. But if you put more gas into a fixed container, the pressure builds in the container. If you put more gas in, it continues to build, and eventually the pressure is too great and the container explodes, which is not a good day. We're supposed to why would there be an increase in pressure by a factor? Why the increase in pressure, and by what factor does the total pressure increase when the reactants completely converted into products? Again, we're going from 2 moles to 4 moles, so I put 2 and 4 in for the ends, and I said that, hey, let's say that it starts at 1 atmosphere. So if it started at 1 atmosphere and the moles doubled, the pressure should double. Whatever the original pressure was, it would double. So it's not actually 2 atmospheres, it's twice the original, whatever it might be. One reason I like to write the ideal gas law this way is I can create a lot of interesting gas laws for whatever the situation is. When I read what's constant, I can kind of cross those mentally out of the equation and just have what I need left. This is a closed manometer. We didn't talk about manometers in the notes. Manometers are instruments for measuring gas pressure changes. This one has mercury in it. We're not allowed to have a mercury manometer. It is closed right here, and at first it's empty on both sides. It says it's evacuated on both sides. So this is evacuated and this is evacuated. So the mercury levels both are equal if the gas sample is introduced into the flask. So a gas is introduced into here. See, it says gas, and then the pressure of this gas is pushing the mercury up. And the way you read this is pretty simple. If it's mercury, you just measure the height. The height of the mercury is 6.5 centimeters. 6.5 centimeters would be 65 millimeters of mercury, and you're done. There it is in torr, converted to pascals, converted to atmospheres. We don't usually work in pascals. We usually work in kilopascals, so this would be 8.67 kilopascals. Alright, so the height is equal to how much the mercury's been shifted. That's it. If it's a closed manometer. We'll talk about an open manometer later. It's slightly different. You have to compensate for atmospheric pressure, but since there's no atmosphere up here, no need to compensate. A particular balloon is designed by a manufacturer to be inflated to more than 2.5 liters, meaning after that it bursts. We're given a volume, and this threw some people off. It's at sea level. At sea level, the air pressure should be 760 millimeters of mercury, or at least that's what they're implying, because standard pressure at sea level is a perfect day. They didn't actually come out and state that, which kind of irritated me. The balloon is released. Animals get poisoned by the remains, but anyway, let's not talk about that. The pressure is now only 500. So now the pressure is 500. What's the new volume? New volume would be 3 liters. So boom, yes, it would explode. The balloon got too big. Brief pause for water. Number 5, we have volume and moles. How many moles? New volume. Pretty straightforward Avogadro's law. Number 6, though, is a little bit difficult. This is 2 containers, unknown gas, no pressure actually given, just PA and PB. So we're supposed to talk about how the pressures are related. We'll take a look at the data real closely. The moles of gas go from 1 to 2, so they're doubling. The volume goes from 1 to 2, so that's doubling. The temperature is in the wrong unit, so I converted it to Kelvin. 280 to 560 Kelvin, that is also a double. So then I thought about how to write the equation I'm using. We have moles, pressure, volume, temperature. The volume is doubling and the temperature is doubling. So I crossed them out because that change would cancel out. If I multiply V by 2 and T by 2, that'd be multiplying by 2 halves, which would be canceled out. However, we are also doubling the moles. If I double the moles, I must also be doubling the pressure. So whatever PA is, you have to double that for the pressure for PB. So PB is twice whatever PA is. You know, that's pretty complicated. Why not just throw a number in for P? Pick a simple number, 1, 5, 10. Don't make it complicated. Just a random number, put it in there. It's always good to avoid actually using 1 just because it can throw you off occasionally in division. But if you pick 3, if you put a 3 in here, did the math, the new pressure would come out 6. And you would see that whatever this P was, the other P should be twice as much. 7. Ooh, 7. Ideal gas, tiny volume. Look at that. That's in milliliters. Okay, actually that's 500. It's not tiny. Convert to Kelvin, torr. Ooh, that is a tiny volume, 25. So if the volume is going from 500 to 25, the pressure is probably climbing. And then the other thing that's happening is the temperature is going from 300 to 1000. So again, the pressure is probably climbing again. So the pressure is climbing for 2 different reasons here. Here I got 51,200 torr after sig figs. Number 8 is just a straight sig gas law question. Make sure you convert to Kelvin before you plug it in or rearrange. That's all you get for that one. Number 9, it didn't photocopy very well. Just 1 second. Here's what the original picture looked like. There was 1, 2, 3, 4, 5 helium atoms, 1, 2, 3 neons, and 2 argons. So that picture just did not photocopy well enough. Sorry about that. So I've written that down. There's 3 neon, 5 helium, and 2 argon. There are 10 particles floating around in here. Sounds like a good time to do mole fraction. Of the neon, the mole fraction for neon, there's 3 neon particles for every 10 particles. For helium, there's 5 for 10, or 1/2. For argon, there's 2 for 10, or 1/5. Mole fraction is just really just a ratio of the particles or a ratio of the moles, but it's also a ratio of the pressures. So now that I know the ratio of moles, I also know the ratio of the pressures. So 3/10 of the moles are neon, so 3/10 of the pressure is from neon. What is 3/10 of 1? 3/10, or 0.3. So I just applied the mole fraction to the total to calculate the pressure for each gas afterwards. Again, mole fraction is the mole of what you're looking at divided by the total. Number 10. Number 10, this I had to I dropped in the color versions here for you. Consider the flask in the diagram. We have 2 liters at 475. We have 1 liter at 0.2. And I thought about this for a while. When I open it up, the hydrogen on this side is going to spread over here, and it's going to go from a volume of 2 liters to a volume of 3 liters, because it's going to be the 2 and the 1 added together. And it's going to spread out. And the pressure from hydrogen is going to drop, because it's now going to be spread out over a larger volume. So I started with the hydrogen. I said, okay, here's PV equals PV divided by the new V. So 475 times 2 divided by 3 is 317 torr. Now I have just realized a tiny error in here. Let me pause for a second. Alright, here's yet another example of me being human. I did not catch when I was looking at this diagram that this was in torr while the other side of the vessel was in atmospheres. And it did strike me odd at the time that this was 475 and that was 0.2, but I didn't actually look at those units. So I did it in purple here accidentally in atmospheres, but I didn't realize I was doing it in atmospheres. So I've redone it in red. So this is 152 torr instead of 0.2. I'm just going to make that float above the 0.2. This side of the vessel was 1 liter. Once it's opened, now the gas can spread out across all 3 liters. So it goes from a pressure and a volume to a new volume. Here is the new pressure, 50.7 torr. Not this other number, how silly. And so that's the pressure from the nitrogen. Then you also have to consider that the nitrogen and the hydrogen are floating around inside this same 3 liters. Well, this part's really easy. We just take the pressure of nitrogen and the pressure of hydrogen, we add them together. So I accidentally did it wrong here because I thought I was doing it right earlier. Scratch. And now we have the right pressure. Here it is, 367. That's the torr from here and that 50 torr added together. Not bad. I did catch it in number 11 though. I want to point out over here on the side, these compounds, these molecules, these atoms are mixing. They are not reacting. We've just created mixtures, not reactions. It's not hydrogen and nitrogen making something. They're just bouncing around in the same space. If there was a reaction, we'd have to do mole ratios and molar stoichiometry, but there's not, so we're good. Here I did actually catch, look, that's torr, that's atmospheres, that's kilopascals, or kPas. So I converted the torrs to atmospheres and the kilopascals to atmospheres before I did the math. I almost did it wrong on this one. See, I caught it. I wrote 200 and I was like, oh, no, just kidding. So here we have our answers. These are in atmospheres, and then the total in atmospheres there. There is a key sentence up here, though. We're assuming that the connecting tubes have a negligible volume, which is to say no volume. We're pretending like there's no volume in this space up here. I wonder if that's realistic. On to B. So the first B question is pretty simple. It's just a PV equals nRT. I'll solve for the temperature. The temperature is 69 Kelvin. No big whoop whoop there. And then in 1B, the temperature is increased. What would the new pressure be? There's 2 ways to do this. I first did it using PV equals nRT, where I throw in the moles and everything, the new temperature, and got my pressure of 32 atmospheres. Or you could say, well, it's going from 69 to 225. That's an increase of 3.23. It's 3.23 times more. So the pressure should increase by a factor of 3.23 also, which it did. It went from 10 atmospheres times 3.23, and now it's 32 atmospheres. So you could do it either way. Number 2 is the airbag question. It's at STP, so I can change the volume into moles using 22.4 liters is 1 mole of any gas. I do have to then convert it, though, to sodium azide, because the question is what mass of sodium azide, so I used the 2 to 3 ratio between nitrogen and sodium azide and converted it to grams. Bam. We're going to talk about your Airbag Lab at the end of all of this. Number 15. 15 threw me for a loop for a little bit. I have 0.5 atmospheres of krypton and 1.5 atmospheres of chlorine mixed together inside the same container. So I wrote a balanced equation there, and then I thought, well, which of these is going to be limiting me? So if I have 0.5 atmospheres of krypton, I would only need 1 to 2 ratio, 1 atmosphere of chlorine. Who says chlorine? So I have an excess of chlorine, and I'm going to use all the krypton up. Well, then I realized if I have 0.5 atmospheres of krypton, I'm going to make 0.5 atmospheres of krypton tetrachloride. So I used that 0.5 atmospheres of krypton tetrachloride. The volume was 15. R, how did I pick this R? This is a common question. R was an atmosphere, pressure was an atmosphere, so R has to be the atmosphere version of R. Temperature in Kelvin. So I solved for moles, and then use the periodic table, and krypton, a rarely used element, I had to look at its mass up. I converted it to grams. Number 4 also has a limiting excess issue. We don't know which one's going to be limiting. We're reacting methanol with oxygen to produce carbon dioxide and water. So I wrote my reaction first: 2 methanols, 3 oxygens, this and this. Now let's be careful here. There's 4 hydrogens here. 3 plus 1 is 4. When I tried to balance it, I ended up with the wrong number of oxygens, so I had to come back and do it again. Multiplied by 2. 2 carbons, 2 carbons, 4 hydrogens times 2 is 8. 4 times 2 is 8. Add them together. 4 oxygens and 4 more. 8 oxygens. This is 6, and then there's 2 more over here in the methanol, and those are the 2 oxygens people usually forget because they're so used to just looking at this in a combustion reaction. One interesting thing here is they give us the volume of methanol and its density. With density and volume, we could get mass. I guess we're assuming that it's pure methanol, which is pretty weird, but that's the only thing I could possibly think to do here. So I said density, volume, mass is 42 grams. That would be 1.326 moles of methanol. Question's really about moles of water, so I used the 4:2 ratio to water, and I got a possible answer. Then I used the information for oxygen. I've got a volume, I got a temperature, I got a pressure, so I PV equaled NRT'd, got the moles of oxygen, used the ratio, 4 and 3 between oxygen and water, and got another answer for water. And the smaller answer indicates when the reaction would run out. It would run out once 2.47 moles of water were formed. Number 5, we have hydrogen cyanide, which is a gaseous molecule that floats around. If it was an acid, if it was in water, it'd be hydrocyanic acid. So it's hydrogen cyanide. I got excited and wrote the formula here, and I shouldn't have. It is made by methane, ammonia, and oxygen at high temperatures, the other product of gaseous water. So I wrote methane, ammonia, oxygen, hydrogen cyanide, and water, and then I struggled through the balancing. This took me a little while. I don't really even remember where I started. I think I started with the carbon. I think I just threw a 2 there and just started playing with it until I stumbled into this answer. The hydrogens were a bit hard to track because hydrogen is in every single molecule there. So 2 times 4 is 8. There are 6 more here. 8 and 6 is 14 hydrogens. I have a 2 here and a 6 times 2, so it's 12 and 2 is 14. And then I can fix the oxygens. In B, we're told we have 20 liters of every reactant. 20 liters of every reactant. And what I realize is that you can actually use Avogadro's law for questions like this if you want. You can kind of think of it as Avogadro's law, where you're doing the mole ratio, though, to represent the moles here down here. So you could say volume of oxygen is 20, moles of oxygen is 3, moles, what are we looking for? Oh, so moles of hydrogen cyanide is 2. So you could say 20 over 3 equals what over 2, and you could solve for the hydrogen cyanide. Given these ratios, 2 to 2, 2 to 2, 3 to 2, the oxygen is going to be your limiting factor, so we just use the 2 to 3 ratio and solve for the hydrogen cyanide. We're not going to make 2 to 2. We're not going to make 20 liters because we're going to run out of oxygen before we get to 20 liters of hydrogen cyanide. 6 and 7 both rely on the molar mass equation. dRT over P, dirt over P equals M&Ms. So I just plugged in chug. I put the density in there. It's STP, so I plugged in the temperature and the pressure. I picked 1 atmosphere for my pressure, so I had to pick the R that correlated to it, which allowed me to find the molar mass. It says it's diatomic, so that is actually twice the mass of the element. So I divided it by 2, and then I found that the unknown element was 35 grams per mole, which is probably chlorine. Uranium hexafluoride. I had to look up uranium's mass. It's 238. Hexafluoride, 19 times 6, added it together, a big 352. That's a heavy molar mass. Plugged all the other pieces in. The pressure, the R in torr. Why did I pick R in torr? That's 62.36. I picked the R for torr because the pressure was in torr. So that way these torr and those torr will cancel each other out. And I converted the temperature to Kelvin and got a density. Coincidentally, this density of this gas is more dense than the density of solid lead. So that's a pretty dense gas, uranium hexafluoride. No thank you. Is that it? Oh no, that's not it. This is the blank page where I messed up. And we have another page. Okay. There's a whole lot of words in this one, really confused me. And then after I read it a second time, I realized that they were collecting the nitrogen over water vapor, so that's going to be wet air. It's going to be wet air, wet nitrogen gas. It's going to have H2O floating around inside the gas with the N2. I just found a little picture, and it's not exactly what we're doing, but it's pretty representative of the idea. It says, as you collect a gas over top of water, some of this space above the water will have some water molecules floating around in it also. So it's not just the one gas, it's your gas you're collecting plus a little water vapor. So what chemists have done is they have carefully measured the amount of water vapor that can be carried in air at different temperatures. So right here it says the vapor pressure of water, meaning the amount of water that vaporizes, 25 degrees Celsius is this pressure worth. So the pressure that's given, this pressure is both the gas and the water floating around. So 726 minus the water gives us the pressure of just the nitrogen. From there I have the pressure nitrogen, volume, R because it's in torr, and then 298 because that's the temperature. I got my moles, I got mass, and then I did a percentage. I did what percentage of the original would be nitrogen. 9 is also similar. You have some oxygen collected over water. Here's the total pressure. When the oxygen was dried, the water vapor is removed. Now the gas is this. What's the amount of water vapor? So this time they're not telling us the amount of water vapor, but they've given us a lot of information. So at the first sentence, 2 liters was collected over water. The total pressure, this is the pressure of oxygen and water. So 785 is both right now. It's the volume, pressure, temperature. So volume and pressure, temperature, this moles we've just calculated is both the oxygen and the hydrogen, and the water, not hydrogen. Oxygen and the hydrogen. Water. Getting tired. When the oxygen was dried, the water vapor removed, the gas's volume changes because that actually took up exerted some pressure in there, so the volume changed as the pressure changed. Here it is. This is the pressure. This is the volume after the pressure adjusted back. RT. Now we know the moles of just oxygen. So if 0.08448 is the total moles, and this is the moles of oxygen, I can do the magic of subtraction to find the moles of water. Then I took the moles. I have moles in a couple different ways. I have the total, I have oxygen, I have water, and I wrote a mole fraction. I wrote the moles of water over the total moles. This ratio should be equal to the ratio of pressures. So this was the pressure total, and this is the pressure of water. That's the mole fraction. That's this divided by that. 0.0025 over 0.08 is the mole fraction of 0.029. That's not very much water. The rest of it is nitrogen. So I know that this pressure over 785 equals that, so I solve for the pressure of water using mole fraction. Number 10 is actually the last question. Hydrogen and nitrogen combined in a 4-liter flask. Good. 0.7 grams of hydrogen, 2.5 grams of nitrogen, placed in the flask and heated. The final pressure after the reaction occurred is such and such. Well, first off, they gave masses, and that's not terribly useful. And I started by writing down the mass, realized it wasn't useful, and realized I needed to write down all of the moles. So I made a little chart here. There are 0.371 moles of hydrogen before the reaction. Alright, so I converted the mass into moles for hydrogen and wrote it down. There's 2.5 grams of nitrogen. Nitrogen's in 2, I converted that to moles. Before the reaction, there is no NH3. Now, one of these two things is probably going to run out first. So I used the mole ratios and I checked. I found that, let me do that, 0.371 times 2/3. I could have made 0.247 moles of ammonia if I base the math off of hydrogen, but of course I'm going to make the smaller value. So when I did the math based off of nitrogen, I could only make 0.1784. So that's how amount of nitrogen I'm going to make. And when I make this 0.1784, I'm going to use up the nitrogen that's present. So there's going to be no nitrogen present afterwards. Converting the nitrogen to ammonia. When you convert the nitrogen to ammonia, you're also getting rid of some of the hydrogen. So to figure out how much is going to react, well, for every nitrogen, there are 3 hydrogens. So what I did is I said 0.0892 times 3, because it would be 3 times that value using the ratio. So there would be 0.26, and then my calculator says 76, but I rounded up to 8 since I'm kind of running out of sig figs here. So 0.268 would react, meaning of the hydrogen, I'm going to subtract this much that reacts, and then these are the moles that are left behind for hydrogen. Now this is key because we have both moles of ammonia and moles of hydrogen both in the container, so they will both impact the pressure. So again, I used the ratio between nitrogen and hydrogen to figure out how much would have reacted and how much would be left behind. Now these moles are in there together, so I added them up together, 0.281 total moles, and I used PV equals nRT, which would give me total pressure. Now, if you go through all this question, it just says final pressure. It doesn't ask for units, so I had to pick a unit. I didn't know which one you would pick, so I worked it out in every possibility. If you use 62.36, you get that. If you use 0.08206, you get this, and if you use 8.3145, you get that. Alright, ladies and gentlemen, thus ends the video that answers all of your questions and a couple more for A and B. Oh, before I kick stop, I was so close to hitting stop, super duper close. Let's look at your lab. Flip all the way to the back. So the very last 2 pages in your note packet there is the Airbag Lab. You can read about how airbags are used. Hopefully you've never had to use one. We're going to be using a resealable plastic bag, not necessarily a Ziploc bag, but some sort of bag. You're going to use the compound sodium bicarbonate and hydrochloric acid. You're hoping to fill your bag to plumpness. Yes. You don't get to say that very often. It's not nice, typically, to say something is filled to plumpness. So you're going to mix the sodium bicarbonate and the hydrochloric acid inside the bag. Trick though, you have to have already sealed the bag before you mix them. So your homework tonight, and take a minute after I'm done talking, talk to your lab partners, figure out who can call who's going to be in charge, discuss. You need to develop a procedure. See right here? With your partners, plan a design for your project and record. You don't need to record it in a lab book, just record it. Come down with a procedure in hand. How are you going to collect data? How are you going to mass things? How much? What? You're going to get all of this equipment that's right here. Baking soda, 6 molar hydrochloric acid, plastic cups, and disposable pipettes. Whatever you need that's not here, just ask me for within reason. Things to keep in mind when you're designing your procedure. Safety concerns. Discuss the hydrochloric acid in your lab write-up. Limiting and excess reactants. You want to make sure that hydrochloric acid is the limiting reactant. You base all of your stoichiometric math off of that. You also need to figure out what the volume of your bag is, so that should be a step in there. How are you going to figure out the volume of your bag so that you do the right stoichiometry? You notice there's not much to this afterwards. You do, when you do your lab report, need to include a complete procedure of what you did. Alright, need to include your observations. It's not going to be as measurable as some of our other labs. I do like some of these post-lab questions, like number 4, your partner grabbed the wrong acid. 12 molar, couple great questions in there. Anyway, you need to exchange contact information so that you can design a lab write-up over the weekend and come in on, we don't see each other again until Wednesday, but come in on Wednesday so that we can get on this lab ASAP. Alright, you guys, talk to you later. Bye.